All right, welcome everyone to the last PHI Colloquium season. Snow is here, chocolates are here, so it's looking good. And today is a pleasure to have David Kaiser with us. David is a professor of the history of science in the MIT's program in Science, Technology, and Society, and professor of physics in the MIT Department of Physics. David completed a PhD in physics and history of science at Harvard University, and his historical research focuses on the development of physics in the United States during the Cold War, looking at how the discipline has evolved at the intersection of politics, culture, and the changing shape of higher education. His physics research instead focuses on the early universe cosmology, like we will see today, working at the interface of particle physics and gravitation.
Thanks so much. Really a pleasure to be here today, both in person and hello to our friends who are joining remotely. I'm really excited to share with you today some work on primordial black holes as dark matter candidates. This might be familiar to some, maybe not so familiar to others, so I thought I would start with a bit of a warm-up, so my laptop lets me. Let's try that. Okay. And so I don't think I need to do too much to convince you that dark matter is a continuing challenge, a big problem in many of our related areas of research. And I won't say much more because we have a terrific world expert on the history of this topic right here, Jaco de Zwart, and I encourage you to check out Jaco's work and more to come. But in brief, just to make a long and actually really interesting story a bit more brief, there's now nearly a century of evidence from different lines of investigation, things like the clustering of galaxies and motions and behavior of individual galaxies of the sort, again, are going to be familiar to folks in this room, that suggests that there's an enormous amount of matter that's not baryonic. It's not made up of particles of the ordinary standard model. And so especially when this sort of problem topic coalesced roughly 50 years ago, again, as I've learned with special clarity from Jaco's work, that there's been kind of three main responses from the community since then. Once dark matter seemed like a big problem that needed a response, one typical response, still ongoing, of course, is to search for some new types of matter beyond the standard model, whether they're weakly interacting massive particles or ultralight axion-like particles, or who knows, there are lots and lots of things in between, again, as you may well know already. So step one is maybe there's other kinds of matter we don't know about. Step two, which gets some attention, not quite as much, would be maybe the laws of gravitation themselves need to be revised. Maybe it's MOND, maybe it's not. What I want to talk about today is actually another approach to that challenge, which also has a kind of robust historical arc going back on the order of half a century, but it's gotten a lot more attention in recent years. And that's maybe it's ordinary matter obeying totally ordinary general relativity, but locked up into primordial black holes. And that's why it doesn't radiate like ordinary matter would be expected to. So I find this actually, ironically enough, to be the most conservative response on offer today to this challenge of dark matter. So suddenly, tiny black holes populating the universe seems like the most straightforward answer, at least one way to think about it, to this long challenge of dark matter. Okay, so there have been waves of interest in primordial black holes as objects of theoretical study of possible constituents of the world. And I'll just review briefly some of those waves. It's a roughly 20-year cycle where you see some greater than average interest. And now we're in this period here where there's a tremendous amount of excitement about primordial black holes. Then I want to talk about some of the most up-to-date observational constraints for black holes as dark matter in particular. As again, you may well know, and I'll review briefly, primordial black holes could exist in an enormous range of mass scales. There's a particular limited range that could be relevant for accounting for all of dark matter. And so those constraints are what I'll focus on briefly here. And then I'll talk about some of the work I've been having a lot of fun doing with some students and colleagues, trying to account for an appropriate population of primordial black holes that really might fit within a sort of sweet spot in terms of the mass range that maybe really could account for dark matter in our observable universe. So the ideas about primordial black holes go back a long way. They're really not such a new theoretical object. In fact, as usual, there are these anticipations by Zeldovich and his group in the 60s, like everything in cosmology. It was done in Moscow and then somehow overlooked or forgotten. The more recognizable form, recognizable even to today's considerations, was written in a remarkably clear paper by Stephen Hawking in 1971. Clear because it speaks even in terms that we might recognize today. The Zeldovich paper was caught up with other considerations at the time. But Hawking's paper from 71 is introducing these incredibly compact objects that should form black holes if general relativity is to be trusted at those scales, and that could form by bypassing ordinary stellar evolution. So you can have some sort of overdensity, some region of space with a much larger than average density of stuff that could induce gravitational collapse, not because you had a star that exhausted its fuel and went through supernova and collapse, but by going direct collapse. And again, as Hawking pointed out early on and developed further with students like Bernard Carr and so many others, that would open up an enormous range of possible mass scales, because the relevant scale for the black hole to be formed then is not set by a stellar mass in a kind of stellar collapse scenario, but it's actually set by the Hubble mass, by the mass contained within a Hubble sphere at the time those black holes formed, and that could be an enormous range. The Hubble sphere itself, of course, is expanding. The mass is changing over cosmic history. So even in Hawking's earliest papers, he points out there's something like 35 or more orders of magnitude that could plausibly set the scale for such direct collapse or primordial black holes. I also find amazing is a very brief paper. Even in this first articulation of primordial black holes, Hawking says maybe this can account for dark matter. Even before dark matter had really become a high-level concern in the community, he was already thinking about things like clustering, galaxy clusters and their dynamics. And based on some early observations from Alan Sandage and colleagues, Hawking says maybe this could account for dark matter in the very first of his papers on primordial black holes. Okay, so this catalyzed
cosmological dark matter.
Yeah, it's certainly a sort of a galactic cluster scale, so not local flat rotation curves. You really had a big. He's worried about the so-called deceleration parameter.
But I think Vicky's census was already there.
Oh yes, yeah, from the 30s.
30s.
That's right. Although as your neighbor Yaka will tell you, that didn't immediately get everyone thinking the same way about dark matter at the time. But already by the early mid-70s, there was some strains coming together to make it look like a particular challenge. So yeah, you can see he's talking about Sandage's measures of the deceleration parameter before we knew it was not decelerating. So you had really cosmic clustering in mind. Okay, so that sort of gets some early discussion going in the 70s. The next really big wave of interest comes in the mid to late 1990s, interest in primordial black holes in particular. Again, some of you might remember this very well. There were a bunch of surveys. One of the most extensive was called the Macho Collaboration for Massive Compact Halo Objects. They had a dedicated telescope in Australia studying the Large Magellanica Cloud and trying to measure lensing events, microlensing in particular. And so the idea was either from objects anywhere along the line of sight in our own Milky Way or in the Large Magellanica Cloud, if there's a bunch of small little compact stuff, if dark matter is some small compact objects, you should have a sort of expected pace of lensing where some dark object moves, along the line of sight. You have this characteristic lensing form for the visible light behind it. And so then you can use those counts to try to bound the proportion and size of these lensing objects. So in the mid to late 90s, they released a very exciting analysis. It could be that the entire fraction of that halo would have been consistent with their measurements. The entire fraction, or at least a majority, could have consisted of tiny compact objects with masses below a solar mass. And that was very exciting because it looked like that would be hard to account for from a stellar collapsed black hole scenario where you'd think the masses would be larger, maybe not much larger, but larger than a half solar mass, maybe more like 3 solar masses. So this got a lot, this helped catalyze another wave of interest in primordial black holes as dark matter in particular, although pretty soon with more observing time, they had to readjust their analysis, and turned out the entire halo could no longer be accounted for by these by objects, at least of that size. They saw too few lensing events with more observing time. And so the same team within a few years said, whatever's accounting for the halo dynamics of, say, the Large Magellanica Cloud, it can't be entirely a population of half solar mass compact objects. So, but that was a blip of interest, more than a blip, in the mid to late 90s. And of course, much more recently with the sort of modern era of black hole physics, gravitational wave astronomy, and all the rest that you folks know so well, again, there's been a real resurgence of interest in primordial black holes as possible sources. The very earliest mergers that were detected from LIGO suggested some curiosities about how to account for black holes in that size, especially as you get beyond the 30 solar mass ones. And so this doesn't prove these must have been primordial in origin, but that led to a new wave of interest in saying, could you account for the population of these black holes larger than solar masses, tens and maybe hundreds of solar masses? Could those have had a primordial origin as well? And so that might not be the answer, but it certainly helps get more excitement in the field. And you can see in this plot by Bernard Carr and one of his colleagues, this is the era where you see an enormous spike of interest, a spike we still inhabit today. Okay. In parallel with all that, and again, this is probably quite familiar to this group in particular, there was a kind of separate set of ideas or motivations that kept some people thinking about primordial black holes for a long time, not necessarily as dark matter, but actually as possible seeds for galaxies, for what we would now recognize as supermassive black holes. And so this goes back also more than half a century, the earliest identification of quasars, and then not too long after that, when Martin Schmidt and others got reliable redshift information, it became clear these were not only bright, but very distant objects. They must have had an enormous source of energy for that kind of output. And that got lots of folks thinking by the 70s about these objects as supermassive black holes, masses set, as of course you know so well, millions or even billions of times solar masses. And then in the 90s, again, consistent with that wave of excitement about primordial black holes between the HST and, of course, much more recently, the folks in this room and beyond, we have unbelievable evidence that all or certainly most galaxies are have at their core a supermassive black hole. And yet again, my understanding is that typical accretion scenarios, Priya has helped me understand over the years, it's actually not so straightforward to account for an object that could be a billion solar masses if it was actually a stellar collapse object that then had only 13 or not quite 14 billion years to accrete. And so one nice idea would be maybe they started larger to begin with. Maybe the seeds were not stellar collapse with a scale set by 1 or 10 solar masses. Maybe they formed at 100,000 solar masses and then accreted 1 to 3 orders of magnitude since then. And so this is an ongoing source of interest among folks who think about primordial black holes, not so much for dark matter, but certainly relevant to large scale structure. Okay, let me talk about some of the current up-to-date constraints. And I should say there's a series of very, very nice, helpful review articles by a series of authors here in the last 2 years or so. Lots more to say about this. But given the best of what a combination of observations and some theoretical reasoning allow, there's right now a kind of reasonable window of about 5 orders of magnitude in mass that for which a population of primordial black holes really could account for all of dark matter. So you can see there's been a lot of work narrowing that range from above and then from below. And yet there remains about 5 orders of magnitude that are still allowed to account for all dark matter.
So, David, I was under the impression that all these observational constraints are for a monochromatic CDH mass and not for mass function.
Thank you,
which
Priya.
is what we want.
Yes, that's a great point. So the short answer is yes, although the mass functions that are to most to be expected, I'll come to this soon, are not monochromatic, but make very small adjustments to this. Some of these now do take that into account as well. The mass function, as far as we understand it, is actually highly peaked. It's not literally monochromatic, but I think it's not enough to change this grossly. So I'll come back to this.
Yeah, when you say evaporation there.
Yeah.
So you have small black holes, they evaporate quickly,
Right.
so they might not persist.
Yeah.
But also, would you expect radiation?
Exactly.
From those? Does that account for both those?
It does, and I'll say more exactly, Chef. So I have some slides on exactly those 2 points exactly. That's right. So I want to talk both about the cutoff here from observations and exactly what Chef asked about here, the cutoff in the small mass size. But first, I just want to say again, this crowd might be used to thinking about both grams and solar masses. I think about neither of those units. I always have to look these up. So as a reminder, a solar mass is around 10 to the 33 grams, 2 times 10 to the 33 I found from Wikipedia. The moon is a bit smaller, of course. These are basically, this mass range is basically asteroids. These are big space rocks. Big space rocks shrunk down to black holes, so their spaceships can be incredibly tiny at the mass is sort of macroscopic on a solar scale kind of solar system kind of scale. Okay. So 5 orders of magnitude is, I think, kind of nicely constrained. It gives us a real region to look at and focus on without being thoroughly open, compared with the current constraints or lack of constraints on particle dark matter. On that first popular option, whether it's WIMPs or axion-like particles or who knows what in between, those still span 50 orders of magnitude in allowable mass for different scenarios. So suddenly 5 orders of magnitude feels really kind of comfortable. Okay, so let's talk about these scales. I'll start with the one Chef was asked about. Just again, as you all know, according to at least a very robust semi-classical calculation, these black holes should radiate from Hawking radiation. Therefore, their lifetime depends on their initial mass. And so one thing you can do is say they have to be around today. Therefore, their lifetime has to be such that they'd still be around nearly 14 billion years after the Big Bang. And that sets a smallest mass to be of an order, not quite 10 to 15 grams. Smaller than that, they wouldn't be here, they could be dark matter. But again, as Shep was just anticipating, you can do even better, by about 2 orders of magnitude better than that, based on the late time evaporation time, so the radiation that would come out. So the temperature will rise as the mass falls. These are inversely related. So as the mass continues to fall from evaporation, the temperature of that black hole should rise. The energy of the decay products should rise correspondingly as well. And so there should be characteristic decay products at high energies if there was a large population of things, in late stage evaporation today. So there are many constraints here, but my favorite actually was just published in 2019. One of them is to look for things like high energy electron-positron emissions. And these are actually hard to detect so close to the sun because the sun is on a magnetic field. So this is what I thought was really clever. If you follow Captain Kirk and use the Voyager spacecraft, the Voyager spacecraft is now beyond the heliopause. It's beyond the immediate effects of the sun's magnetic field, and that can detect, that has E plus E minus detectors on it. So you can use the constraints of the number of high energy particles detected by Voyager beyond the immediate impact of the sun's magnetic field, and use that to bound by about 2 orders of magnitude higher, the lowest allowable mass for these things. On the larger side, so now that was the 10 to 17 grams lowest mass cutoff to be dark matter candidates. On the larger side, you come in from, I'd say, more direct types of observational constraints. And so one of the most constraining comes from the Subaru telescope collaboration. It's a beautiful telescope. It's, as you probably know, it's run by the National Astronomical Observatory of Japan. It's physically based on the Big Island in Hawaii. And they again have dedicated observing time. And in early 2017, the group released analysis, again, much like the 1990s, but with obviously much improved optics and statistics, that you have too few observed lensing events, in this case of Andromeda. If you had this large a population of black holes of such and such size, you'd see more lensing events than they register. So they actually were able to rule out the idea that all of dark matter could be primordial black holes for masses less than 10 to 19 grams. That's around 10 to minus 14 solar masses. And it was pointed out to the group thereafter. They did a reanalysis. Their analysis here was taking the geometrical optics limit, which doesn't work if your black hole has a mass as tiny as 10 to 19 grams, for which the Schwarzschild radius is comparable to the optical light they're collecting at a telescope. I just find that astonishing, right? So some of the black holes are in the tens or hundreds of thousands of angstroms range. And you can't use geometrical optics there. You have to use both finite source and wave optics. And that completely changes the predictions for lensing. And in fact, it adds back in 3 orders of magnitude of allowable parameter space, because it had been inappropriately constraining to assume that you'd have this many lensing events for in the geometrical optics limit. So in fact, as I understand it, the current best limit on the upper end still comes from microlensing, but it's actually considerably weaker than first announced. And that's what accounts for now the full 5 orders of magnitude of kind of breathing room for these things, not just 2 or 3. I find that is a great reminder of the scales involved here. Okay, so it'd be interesting to talk about with the group in general, certainly some of the philosophers of science. To my mind, those are 2 rather different kinds of constraints, it seems to me. So the observational ones they're certainly theory laden. We have assumptions about lensing, we have ideas about a model for lensing statistics, but those aren't highly model dependent, right? Those are kind of, let's say, weakly model dependent up here, like with the Subaru telescope bounds. Over here, we're really taking kind of a semi-classical calculation of Hawking radiation at face value to arbitrary energies, and that might be fine. But that seems to be depending on, I'd say, it feels more strongly theoretically bound up to me as a set of constraints than we should see big rocks at bedlocks, right, which is sort of what's happening here. So that's not to say that the lower bound is inappropriate, but it just seems to be a different kind of reasoning that I find interesting to think about when we look at this kind of parameter space. It's different types of constraints. Okay. So let me talk a bit about how these things. Oh yeah.
Does spin come into this at all?
It's like you saw this, like my next one.
Oh, so is this in centimeters?
So this well would be thousands of angstroms. And so, it's 6,000 angstroms, so it's 1,000 angstroms, that's 10 minus 7 liters, and the minus 5 centimeters, maybe I got that right. The tiny.
10 to the minus. These are subatomic.
Yeah.
Like 10 to the minus 5 centimeters.
I believe that's
squared.
right.
That's the biggest.
That's the biggest. That's right. And they go down 5 orders from there. Yeah, so it could be basically angstroms, tens, hundreds of angstroms for the, say, the short chain. They're really tiny. Yeah. Okay, so how do they form? How might they form? Again, remember, this is direct collapse, not stellar collapse. And so they form from local overdensities. And it turns out you only need to be sort of 40% overdense, not many times overdense. This has been known in the numerical relativity community. It might be well known to folks in the room. It's newer to me. This has been studied now for nearly 30 years with numerical relativity, confirmed over an enormous range of mass scales numerically, 10 orders of magnitude, that this simple, remarkably simple scaling relationship holds. And what's amazing is there's some critical value for the overdensity. It's modest, let's say 40% over, say, the average neighborhood density. Not many orders of magnitude overdense. And then once you exceed that overdensity, there's a kind of critical phase transition with a universal scaling exponent. It looks just like StatMech. I find this amazing. And again, that's something that was discovered by the numerical relativists and review articles on it. What's also helpful for people like me is that we can diagnose whether an object will collapse to a black hole within linearized perturbation. We can't study the entire process, of course. That's going to take the full nonlinearity of field equations. Yeah.
What I recall of Chopwick's work, at least,
Yeah.
is mostly it was all spherically symmetric models.
Yes.
So is this limit really valid for a generic perturbation?
Thank you, Ramesh. That's a great point. So you're right, in the earliest studies were highly simplified.
Yeah.
I would go, so I'm not an expert. I would go to things like the now 20-year-old review article and more recent work since then. Certainly, there's been a lot of simulations that do not assume spherical symmetry since then. The earliest ones 30 years ago was hard to do. So my understanding is this has been tested with much more modern techniques, loosening the kind of simplifying assumptions. It's a great one. I don't know the most recent literature on that, but my saying this has been tested quite extensively since then. So put it that way. So what I was saying a moment ago is that you can diagnose the onset of collapse within linearized perturbation, which is great. So I don't have to worry about these things. It's just used mathematically. So you can't follow the full, progression of this. For that, of course, you need the fully nonlinear field equations. But to diagnose, will this collapse? Will this trigger collapse of a black hole? We can answer that question with some confidence within linearized perturbation, which is amazing. To Shep's question, these are expected to form with zero spin. They're forming from scalar perturbations, not very spinning. They're forming from from the peaks in basically a distribution of Gaussian fields, highly spherically symmetric overdensities. And they're not forming with a kind of massive accretion. They're not immersed in a system with a big accretion disk like a stellar system would be. So again, folks are studying this much more carefully than I have. My understanding is for black holes that are this small in mass, that formed by direct collapse from scalar perturbations, they're expected not to be Carrier. So they expect to have essentially zero angular momentum. And that's something where I'm not the expert, but that's my understanding.
And this is in the matter-dominant area.
Even in the ones I can think of in the form of radiation. Yeah, I think it's independent of the equation of state for this plane here. That's my understanding. Good. So there are little tiny ones with zero or certainly subdominant angular momentum. And coming to Priya's earlier question, they are formed, as far as we can tell, with a non-trivial mass distribution. That's nonetheless pretty highly peaked. These look, if you squint in a linear plot, they look fairly Gaussian. What's really lovely is, in fact, they're not. It's now a log plot of the same distributions. The distribution falls out very rapidly for masses above the typical mass, which still matches Bernard Carr's pencil and paper estimate of 1975. I can't do that. They form with roughly 20% of the Hubble mass at the time of formation, and that still holds with all our fancy updates. But they have a very gentle tail, so you make fewer of them at smaller and smaller masses. You make very few of them at larger masses. And if you make a linear plot, this looks vaguely Gaussian, but it has really some non-trivial features to it. Again, this has been known in the literature for now about 25 years or so. And I'd be glad to share this slide. And so if we want to get black holes in this sort of remaining sweet spot to account for dark matter, that corresponds to times when the Hubble mass was of a calculable size, and we want 20% of that roughly. That means this population had to form at really, really early times, right? A tiny fraction of a second after the Big Bang. And so long before, in particular, say, Big Bang nucleosynthesis, which starts at roughly 1 second, right? So these things are really, really early remnants. If they're going to
aftermath of inflation, right?
So, for example, yeah, that's the direction that my colleagues are taking. Good. And so, again, as if someone saw this coming, thank you for that. And so, what I've been working on with my students and colleagues is trying to understand spectra from very, very early universe physics, spectra of perturbations that really could lead to this population of primordial objects. And so, again, inflation is probably familiar to many of you. I won't linger on it, but I'd be glad to say more. And so I'm going to be looking at a phase of the so-called slow roll evolution during inflation, when perturbations are being amplified and stretched, in fact, beyond the Hubble radius. And we want to study the pattern, the spectrum of those primordial perturbations. So again, this might be well known to many of you. There's now really a very beautiful theoretical apparatus, a gauge invariant apparatus for studying these perturbations to at least a linear order. And so, of course, this won't surprise anyone here, we have to worry about perturbations to the space-time metric and matter field fluctuations, quantum fluctuations, and so on. And so we can combine them into linear combinations. Common one is the gauge invariant curvature perturbation. That's proportional to what's called the Mukhanov-Sasaki variable. That's basically a gauge invariant measure of the matter field fluctuations directly proportional. And then, as we do all the time in primordial cosmology, we can linearize the field equations, the general relativity field equations, for these very carefully selected gauge invariant quantities, like this gauge invariant scalar curvature perturbation. And then it satisfies a remarkably simple looking wave equation. So we're going to linearize the field equations to start, at least we can go beyond linear order too. And then again, this might be familiar to many of you. What's quite remarkable is that if you just stare at this equation long enough, or go to some review articles if it's newer material, the behavior of these primordial perturbations depends strongly on whether their wavelength is shorter than or longer than the Hubble radius, and their behavior changes qualitatively through those transitions. So at early times, if we want to follow, for example, the coding length scales, a wavelength that will eventually re-enter the Hubble radius at the time the CMB photons are first emitted, if we want to choose that length scale to look at, so it equals basically the horizon scale at 380,000 years after the Big Bang. That's an interesting time for us to think about. Trace that perturbation backwards in time to a time when its wavelength was much shorter than the Hubble radius. It's oscillating around, obeying this equation. It's essentially a harmonic oscillator, a non-harmonic oscillator equation. At some point, the mode will redshift, its wavelength will become longer than the Hubble radius, after which the mode stops evolving the linear order. So the amplitude of these modes gets frozen in at Hubble crossings. And so what you want to do is study the statistics of these distributions around the time of Hubble crossing. The amplitude, 2-point functions, 3-point functions, you go to higher order if you need to. And then that's kind of carried forward basically for free, to be simple, until those modes re-enter the Hubble, until the Hubble radius catches up with those modes again. It's quite lovely. And so that would, for example, map the local inhomogeneities in the universe from the very earliest moments to what would eventually be seen, for example, in the temperature anisotropies, the CMB. Okay. So that's for one scale. What if you have a second scale in the problem? And so, for example, what we want to do now is we want to make little lumps in the early universe that are going to be visible in the CMB. On an exponentially shorter length scale, much smaller length scale, we want to have other bumps that can do other things for us, like have large overdensities that can collapse into primordial black holes. We want all this to happen before inflation has ended, at least in these production mechanisms. And so you have to worry about the dynamics around the time when certain CMB relevant length scales are exiting the Hubble radius. You also then want to worry about the dynamics when some much shorter wavelengths are exiting much closer to the end of inflation, because that's what's going to set the statistics for these other short wavelength moments. They'll re-enter early, the other ones re-enter late. So that's the kind of scenario we want to think about. Okay, so first, just for the CMB, again, is probably well known to many of you. The CMB has been an amazing source of information, even though it is essentially a two-dimensional snapshot. And so with data like from the Planck collaboration, of course, many collaborations, some ground-based, increasingly by satellite, there's not just one or two numbers, there's now sort of 6 independent measures, many known to better than percent level accuracy, that any model of the early universe has to be consistent. Okay. So it's not just, is the universe basically flat? It certainly is flat. Is the spectral index nearly flat? Yes, but with very, very carefully measured deviation, perfect flatness. It's not literally just white noise in your universe. There's a running of the spectral index and so on. Lots and lots of information here that we have to think about for these scales, my purple line here. So you have to remain compliant with that and then see if you can do anything else at a different length scale. Okay. So to produce these primordial black holes, you have to have a very significant overdensity. It's still within the linear regime. The power spectrum is still much, much smaller than 1. That's enough to diagnose with this collapse of a black hole, but it's about 1 million times larger local overdensities than the CMB, right? On much, much, much shorter length scales, actually exponentially shorter, about e to the 40 shorter in the way of light. And so it went by quickly. This gauge invariant curvature perturbation is proportional to this measure of the matter field fluctuations and the numerator, and inversely proportional to the rate at which the expansion itself is changing. So epsilon, as you may know, is the change in the Hubble parameter per Hubble time, basically. So how much is the rate at which space is expanding itself changing? So that's in the denominator. So if you want to make this thing really big on certain characteristic length scales, you have basically two options, right? You make the numerator really large, or you make the denominator quite small for specific length scales to make certain perturbations amplified compared to the other ones. So a common tactic that's been known for, again, 25 or more years is to try to make the numerator temporarily large. Let's say the modes of certain characteristic scales become very large. And one example would be, say, there's a temporary change in the effective potential so that certain modes experience a temporarily tachyonic mass, a negative mass squared. They'll grow exponentially in amplitude, but not all modes will, just modes whose wavelength is crossing outside the Hubble radius around the time that these dynamics have switched over. That will amplify those modes, but not modes that have been evolving much earlier during inflation. That's one example. You can change the dynamics of the matter field fluctuation. You can make the numerator really big on characteristic length scales. Or you can target the denominator. That's become very common in the field as well. You can try to make the dynamics during inflation go through a temporary but dramatic change, changing the rate at which space itself is stretching. And so, for example, if the fields are evolving in some gentle potential and they come to a quasi-inflection point, the kinetic energy will fall even lower than it has been. In fact, it can fall exponentially. That's the slow roll parameter is directly proportional to this kinetic energy of the system flowing through this potential. So if the kinetic energy itself drops by many orders of magnitude, that'll amplify the perturbation spectra on characteristic length scales because you're sensitive to dynamics when those modes are exiting the okay? This is often now called ultra slow roll evolution. And so each of these have been well studied in the literature, often as, if not quite toy models, as let's say proofs of principle. That each of these mechanisms could happen, they could lead to, say, a million-fold amplification of the power spectrum. You could tune them when they would occur. These are feasible things to happen within kind of simplified toy models. And what I was curious about with my students and colleagues was, see, are those phenomena to be expected? Are they reasonably generic based on what else we might know or expect from high energy physics? And so a lot of the fun, frankly, has been trying to fit these very kind of simplified single field toy model, almost kind of, I don't say cartoons, proofs of principle, into a more robust embedding that is consistent with more of what we know about what we think we know about behavior matter at very high energies. So the first thing that strikes many of us is that every successful theory we have in high energy physics, including the standard model, is actually a multi-field model, even multiple scalar. The electroweak sector actually has 4 interacting scalar degrees of freedom at high energies. We often mention the single Higgs field, the Higgs boson, but actually in renormalizable gauges, all 4 modes stay in the spectrum. The Goldstone modes are there too. Even the beloved and well-tested standard model is a multi-scalar field model at high energies. Every known extension or hypothetical extension beyond any so-called beyond standard model has even more scalar degrees of freedom at high energies, whether it's supersymmetry and even more exotic things or interesting things that might come from string-inspired work, Axiverse and so on. So the early universe should have been awash in interacting scalar fields, not just a single scalar field, but multiple, probably many more than even just 4. That's sort of ingredient number 1 that my colleagues and I have been eager to try to incorporate. So it's not just a kind of single field proof of principle. The second of what I would consider fairly generic ingredients for any modeling of the early universe are these non-minimal couplings. Again, these might be quite familiar even from classical general relativity. But it turns out any self-interacting scalar field will induce these non-minimal couplings to the space-time Ricci scalar in the effective action, even if the coupling vanishes at tree level. They'll be induced by loop corrections if they weren't there to start. And in fact, the strength of this dimensionless coupling generically rises. It rises with energy scale under renormalization group flow. It has positive beta function. So these things have to be there in general, and they need not be minuscule at high energies in the early universe. So we've been taking these two kind of general or generic features, more than one interacting scalar field, each of which has this sort of hard to turn off or avoid non-minimal coupling, and ask, do models with those more general starting points yield interesting dynamics during inflation that could maybe answer these questions about things like primary black holes and dark matter. And so if we were to start to model a system up here that has more than one interacting scalar field, we'd write down an action with the ordinary Einstein-Hilbert term for the gravitational degrees of freedom. We have multiple scalar fields. My capital I and J are labeled different field flavors if we like. They interact together. Once we recognize these nominal couplings will be induced, even if they're not there at tree level, they might even be there at tree level, then our action has this modified form for the gravitational sector. It was originally often called a Jordan-Brand-Sticky-like term. That's actually quite generic for these high energy couples. And so we could begin with that effective action, form a conformal transformation to get the gravitation degrees looking familiar again, partly because of this amazing apparatus for gauge invariant gravitational perturbation theory. So one, it's not required, it's convenient to have this thing look as familiar as it can, because this whole machinery for matching predictions from inflation with observations is really worked out especially conveniently with canonical gravity, but we can't get away for free. We just have to reshuffle the kind of complications into the matter sector. And so by performing this conformal transformation, we make gravity look ordinary again or familiar, but now we have non-canonical elements of how the matter fields behave. For example, a modified kinetic term, and also, as I'll show in a moment, the potential energy is modified as well, all just by performing this conformal transformation. So if the original potential were in, again, a fairly simple starting point in the so-called Jordan frame, with just a series of polynomials, an m squared phi squared, a lambda phi fourths, a combination of more than one field, it's going to look typically like some bowl, right? Once we perform this conformal transformation, the bowl gets stretched in the Einstein frame where gravity now looks canonical. The interaction potential looks pretty funky. It looks lumpy, in fact. It's going to have a series of local minima and local maxima because it's stretched by this conformal factor. And to make these more obvious, you can then move, if it's a two-field model, for example, move to polar coordinates. These two are the same function, just plotted in different coordinates. The original fields, let's say phi 1 and phi 2, versus say r and theta for the field space. So you can see you generically get these ridges and valleys in the effective potential, whereas originally you had a fairly featureless bowl. And that really comes from keeping the gravity sector look as familiar as possible and pushing the complication into the matter sector. So with a quite wonderful former PhD student finished some years ago, Evangelos Sakianakis, we began studying the dynamics during inflation of these models. We have these lumpy potentials in the Einstein frame. And we found this attractor behavior, which is actually pretty straightforward to understand. If you imagine plopping down your marbles anywhere on this potential, they're going to very rapidly find a local minimum. These local minima tend to be basically straight lines in field space. The system will evolve as if it's an effectively single field model, because the potential now has some structure to it, local maxima and local minima. And so you have this behavior that means that the predictions for the model have actually very, very weak dependence on things like conditions, or in fact, even uncovered. Once you find the local minimum and you zoom toward the global minimum, the dynamics sort of don't care very much that you actually have many interacting degrees of freedom. And so, for example, what that tends to do is land you right in the sweet spot of the measured values for the CMB. This is from the Plot 2018 collaboration, and you might not stare at these plots so often. This is a plot of the spectral index, the degree to which the power in these primordial modes shift with wavelength. It's just very, very minimally. N equals 1 would be white noise, a flat spectrum. We have now a very carefully measured deviation from perfectly flat spectrum, but it deviates very little, on the order of 5%. And on the the vertical axis is the ratio of power in primordial gravitation waves to primordial scalar mode perturbations, so-called tensor scalar ratio. This has not yet been measured, so it's getting better and better bounded. There can't be this much or more tensor modes because we haven't actually found primordial tensor modes yet. And this has now been measured to better than percent level accuracy. So we often have to stare at these NSR plots. And the models that I was just describing generically put you here. And the little wiggle here is a little uncertainty in what happens immediately after inflation, so we call the reheating phase. I think that's like that's why there's not only a single dot, there's a little bit of wiggle room left in how rapidly the universe thermalizes after inflation. That has a little nudge on how we map the CMB sky to modes during inflation. That accounts for this last little wiggle compared to the rest of the parameter space. And in fact, these predictions for models like I just described vary very, very weakly with both the field's initial conditions or even the couplings of the model. And also for the cognoscenti, if you have more than one interacting degree of freedom, more scalar fields than just one, you can have quantum fluctuations in more than one direction field space. And you have to worry about overproducing perturbations in directions orthogonal to the general flow during inflation. Those are called isocurvature modes. Those would show up as departures from a purely adiabatic spectrum in the CMB. That's now highly, highly constrained. If the system evolving as if it were effectively a single field model, then those get exponentially suppressed, the so-called isocurvature modes, and likewise for non-Gaussian. So these models have some features that I already had found really quite lovely. They incorporate what I would consider interesting or relevant features from a kind of theoretical starting point, and they are really, I think, quite robust in terms of matching to the CMB sky. Okay, now we want to see, could we start from there and have some other dynamics much later during inflation, closer to the end of inflation, that could yield quite different dynamics for length scales exponentially shorter than the CMB sky that could maybe see primordial black holes. So what we started with was actually a quite generic effective field theory. Throw in every dimension 4 operator that you can think of that includes nominal couplings, includes all the couplings you want, and then see what types of interactions you might expect from it without putting them in by hand. And so to make it concrete, we adopted a particular supersymmetric model. It's actually not highly dependent on supersymmetry. We're really just taking all the operators you might expect on kind of dimensional grounds that are not wildly violating any symmetries you might expect. And then you get a series of terms in the effective potential in the Einstein field. And so you'll expect terms that go like a lambda 5/4. There'll be cubic terms, there will be mass-like terms and cross terms and so on. And so once again, we can then perform the conformal transformation. We keep gravity as familiar as possible. Consider how these more generic series of terms will interact at both large length scales and shorter length scales. Once again, you get these very clear divisions between ridges and valleys. This system can evolve as an effectively single field model. Here's the angle and field space the system will evolve. Only toward the end you have a kind of degeneracy in field space. But now, by having all these different couplings in the mix, you much more generically going to find these sort of quasi-inflection points. You don't put one in by hand. You have a series of couplings, and if the couplings go in here, there's typically some region in field space for which the couplings here will be comparable to the other terms. You get a near cancellation, a near or quasi-inflection point. And that can slow down the system's hurrying rush toward the global minimum. It can encounter this tiny, tiny period of ultra slow roll evolution where the kinetic energy drops exponentially small. That should amplify the power spectrums. Not because we put it in by hand, we were starting with what we considered sort of vanilla type starting points in a multi-field model. Then you can run this through and say, well, what should we see on the CMB sky from these models, and what else could you get out? So here's the dimensionless power spectrum as a function of the time before the end of inflation. It's number of E-folds of inflation. This dashed line is the amplitude you need to match for the CMB. And so you need to match that when perturbations of the relevant length scales first cross the Hubble radius. So you can tune your parameters to pin that. If you're wildly off from that, then stop. Then you can ask, will the system then hit one of these quasi-inflection points? Will the spectrum undergo this exponential increase in power over exponentially shorter length scales? Will it cross the threshold to induce collapse in primordial black holes at the right time to make black holes the right size? So far, for the choice of parameters here, the answer is yes and yes. You can make sure the spectral tilt is within the 2 sigma bounds of plot, which is now known as the better than percent level accuracy. The running of the spectral index is actually not yet highly constrained. It's easily consistent with that. That will improve over next generation.
David, this has to be finely tuned.
It does. I'm absolutely agree. You're right. And I'll say more about that in a moment. We're concerned about that too. Lastly, you can't overproduce the primordial tensor modes that would have been seen by groups like BICEP. We've actually seen groups like BICEP, we can say tongue in cheek. So it turns out there are actually 8 specific observables to match with only 6 free parameters. That includes the field's initial conditions. That's where this attractive behavior really helps. If you have to incorporate every single initial condition for every field, and that had a big variation on your observables, then you could fit anything, right? You'd be overfit. Here we're fitting 8 things, 7 of them to better than percent level accuracy, to 8 particular observables. With in this case, 6 sort of tunable parameters. Now to Priya's point, you're quite right. What about how much give does the system have? So to get this to work, this took a lot of playing with Mathematica, a lot of late nights by me and my really quite wonderful colleagues. Does that do it? Does that do it? Does that do it? Nudge, 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 nudge. Because you want to get this, you want to get the peak just at the right timing to get the black holes at the right size for dark matter. And that was hunt and peck, to be honest. And then someone realized, oh, computers do that better than we do, which was true. So now we're almost done with this follow-up, doing a Markov chain Monte Carlo analysis, the same model, but now it turns out you can let each of those parameters float within around a 10% error margin, instead of fine-tuning one to a high, unnatural degree. So you keep matching all 8 observables with still only 6 free parameters, and yet they are these non-trivial kind of region in the parameter space. It's not delta functions. It's not just you found one parameter that worked. There's some give in the system. I think that is still due to the fact that to match the CMB, there's a lot of you can get away with a lot because it's attractive behavior on the large scales. So the trick is actually matching the short scales, and you can do that not with any old choice, but not with sort of delta functions either. I found that very encouraging. This is now after 2 million walkers in CMC. We're just right now. Now, near the end, the last main thing that's also, I think, very exciting is how might we know? So far, this could be a just so story, right? This model could produce black holes of the size which people say they need. And so, that's all a kind of post hoc analysis. At least one might be worried about that. So there are new observables that should come out of this whole scenario. If inflation happened and there was this production of a large population of black holes of characteristic sizes to match dark matter, then you can't help but excite primordial gravitational waves, stochastic gravitational waves. The waves will be sourced at second order. These have grown to be 1 million times larger than the CMB scale. You can't help but see these in next generation gravitational wave detectors, or where there'll be specific frequency, a real spectrum to it. So where should you look? It turns out if you're going to make black holes of the right size for dark matter, then you know the wave numbers at which these things are going to be really big. Otherwise, you haven't crossed the threshold to make those primordial black holes of those masses. So now you know the frequency range to be looking for as a source for tensor modes. At second order, the curvature, the scalar modes will induce tensor modes.
These are ground-based gravitational.
Well, so it includes the sensitive to LISA. These are next generation detectors.
LISA will be able to detect these?
Yeah, well, if we believe, oh, I'm sorry, no, LISA would, I'm sorry. Oh, and not because of the amplitude, because of the frequency. Yeah, thank you, that's right. So this is Einstein telescope into SIGO. I don't know much about these
Ground-based.
missions. LISA obviously is space-based.
Einstein telescope was space.
I think it is a
It's ground.
Ground?
Einstein is ground.
Because these have, the rest of these have to be high frequency detected.
Yeah, so we're looking, the spectrum that our predicted spectrum is peaking at around, 10 hertz.
But these, I'm sorry, do these come from interactions like these are binary of
Oh,
primordials?
Thank you, Chef. No, I should be clear.
The creation.
This is from the modes that induced collapse to black holes, were large enough ever themselves. That at second order, you have 2 bigger than average, modes in frequency bands. That will source tensor. So it really is just the scalar curvature was higher than average. It had to be to cross that threshold to induce collapse to black holes. It's a direct collapse. It's not stellar. Right? Whether those things ever find each other or not, you've already amplified the primordial curvature perturbation scalar, and 2 scalars make a tensor.
And do they find each other, or are they just too sparse to ever?
So that's right. So they find each other.
Abundant.
Yeah. So you can match the dark matter abundance. They're actually quite rare events to make. So you make less than one per Hubble volume at the early time, so the Hubble volume grows. So today we should be awash of them, but it doesn't mean they'll find each other early, right? So it's a rare event to actually induce collapse at 10 to the minus 16 seconds. They're not close neighbors when they. Will some of them find each other and merge? Yes, people have been doing studies, but that's
Fascinating, because then what that means, right? Am I understanding it correctly that not every supermassive black hole that we see today could have been seeded by these guys, a small fraction of what we see today, right?
Oh, in fact, Bree, I've given up on supermassive black holes for the time being. These are all, because these are asteroids. Right? This would be to account for the dark matter. Remember, those have to be much exponentially smaller than even a
But
single
David,
solar
one of the
mass.
problems with PDHs is that how do you stop the accretion? Yes, you form them very early,
Yeah.
but then they're around when matter domination starts.
Right.
And will accrete,
Yes.
right? So that has often been the issue, like how do you actually stop them from?
Well, it's a great point, Priya. And again, folks in the room will know this much better than me. My understanding is when the initial formation is exponentially tinier than even a single solar mass, the accretion rate's very tiny. Think about the targets, going back to Amy's question. The cross section in the sky, right? It's angstroms. So in terms of what's going to fall onto that thing, it's not sucking up its surroundings very readily at all. So I've done some very quick and dirty calculations with a different quite wonderful PhD student, and the accretion rates look to be they'll accrete percent of the starting mass over cosmic level timescales. Other people do that more carefully. We're just trying to get it kind of.
I mean, depending also on the environment, so information depends on where they land, right?
Yeah, but quantity accretion goes like M squared.
Right.
So I think, David is that smaller the mass.
Yeah. I think it was just like
Okay.
what's going to fall on this thing. If this thing is tinier than a proton, it's not.
And then the cross section is
It's tiny.
It's extremely tiny. Again, it goes back to Andy's point earlier. So I think these ones for dark matter, they will accrete, but modestly, slowly, and not to change their behavior qualitatively, as I just said. Others will look at more carefully. That's my I'm saying from their studies. Now the supermasses would be super fun to get back to, and I mean this is a separate challenge. The problem there, I basically done. So let me just say very quickly, the problem with the supermasses is that the earlier you push this peak during inflation, the more likely you are to mess up all of this.
Right.
So it's actually quite a challenge, at least in the mechanisms we've looked at, it's quite a challenge to get the peak here to be early enough that when those modes cross back in, it's later after inflation. So the mass is now, 1 to 10 to the 5 solar masses in a tiny fraction. Once you do that, you're deforming the dynamics closer and closer to the things you better not touch. So I'm not going to say it's impossible. It's a much more difficult problem if the mechanism is something like this. Whereas here, we've really taken advantage of about even the 40 difference in length scale when these modes cross out compared to the CMB relevance. And that's why we can keep this within compliance within 2 sigma. Even that's hard for some models, right? And yet make these very tiny black holes.
So, I think I'm missing something, right? So you are trying to explain all of dark matter.
Yes.
Shouldn't these then be quite abundant?
Yes, that's right. And so they were rare when the Hubble radius was, this big. And so you get very few per Hubble radius when they form, and the Hubble radius then increases by exponentially. So now you have, let's see, when I can go back to, well, I guess I'll have the next plot here.
we said about 0.2 of the Hubble now.
Yeah, at the time of formation. And Hubble mass at the time of formation is exponentially smaller than today. So this takes into account the again, it's based on a monochromatic distribution, though I think that doesn't lead to much deviation from the basic pattern here. This really is saying to match the present day abundance of omega CDM is whatever it is from that we know, could those all be black holes of this mass? This is what's allowed for that to be the case. And those might not interact off with each other. Okay. So let me summarize here. I think these things are pretty awesome. I think it's an exciting area of research. More to be done across a wide range of mass scales, but it feels usefully constrained. It's not totally open compared to, frankly, all my friends who are diligently and carefully trying to figure out some new type of particle or maybe more kinds of matter beyond the standard model. Here again, look at the level of constraints here compared to here. I like living here. This feels like I can do something, not just. Okay, so that's step one. These form again, I think these are fascinating. They're not a stellar collapse. It's a direct route to black holes. It's been tested numerically across 10 orders of magnitude for the mass scale. That universal scaling exponent holds. Is really, I find that astonishing. And so I'd love to learn more about that myself. With this non-trivial, though still highly peaked mass spectrum. So these models that start with things that we think we need anyway to account for very high temperatures, very early universe physics, those indeed have robust regions of parameter space where we could match the CMB sky, which means like 6 numbers, percent level accuracy, not 1 or 2 things, and also produce a population, a large population of these objects with the right masses, right, for this targeted pattern. And hopefully we can learn more soon. This would be, I'll learn more about these different telescopes and other details. But if these sensitivity curves are to be believed, the design specs are going to hold up, then this should be a really remarkable signal to noise type detection event within hopefully roughly 10 years. So, thank you.
Dark matter is really pebbles.
It's really
Pebbles. It's pebbles.
pebbles. Yeah,
Angstrom size.
right. Well, it's asteroids that are the size of a proton. I mean, it could be something.
What's the number density that you expect to do?
Oh, good. I'd have to work it out, but it would be that goes into these plots that I showed you here. Let me check that. Off the top of my head, it's a great question. And we could probably work it for the particular steps.
I saw this question about spin.
Yeah.
I know that things in the early universe and on such small scales may not have observable angular momentum, but it's hard to see that something would collapse without taking any residual angular momentum and then seeing it manifest as spin. So what is it about these collapses in the early universe that prevent any spin distribution?
Jeff, thank you. So this again could very well be an oversimplification. Others have worked on this more directly, so I don't. I'm sure there are things, details that I'm not. The idea is these are forming within an otherwise nearly homogeneous plasma. Right? This is happening well before Big Bang nucleus. This is happening before the QCD transition. It's collapsing of pure quarks and gluons. It's a quark gluon that's uniform to 1 part in 100,000. It's not a lumpy universe, right? The primordial universe is unbelievably smooth, and you have scalar perturbations, local overdensities with no angular momentum of its own, coalescing within what is essentially a nearly unperturbed FRW vacuum. So, and they're forming in less than 1 e-fold expansion. They're not sitting there and then spinning something around. They're forming really rapidly on cosmic timescales of their own relevant, of the timescales when at the time they're forming the cosmic timescales. And they're forming within a featureless mush. Right? They're forming 10 to the minus 21 to 10 to the minus 16 seconds. There aren't protons. There's not pions. And so it really is forming within a very barely perturbed plasma of essentially quarks with most of it. And so there's no lumpiness around which you could have some sort of non-trivial angle. Now again, one can characterize that more carefully, but that's the cartoon version to start with. They're forming within, you have a local overdensity with a featureless plasma.
Right.
Oh, yeah.
So I'm not sure I quite got, I mean, there are two numbers you mentioned in your talk.
Yeah.
Which kind of didn't quite resonate for me.
Okay.
So you said you need 40% over density
Yes.
to make this black hole.
Right.
But the other part of your talk, you said you need a perturbation of 10 to the minus 3.
Wonderful. Thank you.
What's the connection between those two numbers?
That's a great point. Thank you. Okay, so they're different measures and they're related to each other non-linearly. Let me try to get back there quickly. It's an excellent point. Yeah. Here. So this is a direct measure of the overdensities on the screen. This really is basically, rho minus rho back and spatial average. But, this is a direct measure of an overdensity rho, delta rho. This is a gauge of variant curvature perturbation. These are not directly proportional. They're related. They're directly related, but they're related in a nonlinear way. And in fact, a value of the overdensity 0.4 corresponds to these things that we calculate from the early universe that really is genuinely perturbing at the percent level, meaning it's on the order of 10 to the minus 2. And so you have the power spectrum for these things to cross the threshold around 10 to minus, the power spectrum around 10 to the minus 3. to correspond to these scalar overdensities to be above the critical mean. So they're two related measures, not the same quantity.
Is it like a square root between the two?
Yes, with some gradient terms as well. Yeah, it's yes, that's right. So there's a nonlinear even at their between their magnitudes, but there's also, it depends on how you spatial average this thing. There's some essentially gradient information there as well. And so that's what it comes down to is we calculate these during inflation, these freeze out in amplitude and so on. And we relate those. It's not that we don't know how to, it's just it's not a one-to-one, it's not a direct linear relationship between those two.
I had one other question.
Please.
So, you were talking about these generic multiple fields
Right.
giving you ridges and valleys.
Yes.
And then, so, you were saying that you'll quickly come down to the nearest valley.
Yeah.
And then it's almost a linear path
Yes.
along the bottom of that bowl,
That's
not
right.
bowl,
Yeah.
the valley.
Yeah.
And then you do your stuff.
Right.
So, and then you said, so for an interesting class of problems, you can have this inflection point, right?
Yes.
And that's where all the good things happen for you.
Right.
But it would also have multiple ups and downs. I mean, I should imagine. Why an inflection?
Good. Thank you very much. Another good question. So let me see.
I mean, you mean the local minimum?
Yeah.
Yeah.
Having come to the bottom of the valley, I don't see why it has to only keep going down. It could also go up a bit.
It's absolutely. No, that's right. And so that's a choice of parameters too. No, you could be worse. You could actually have a local minimum and a local maximum.
That's
just
what I'm
along the
thinking.
direction.
Yeah.
And then the system might not have enough kinetic energy to escape classically. Maybe it tunnels out.
Yeah.
That's bad news for the universe.
Okay.
If it does that, because then you have a high that wouldn't look anything like we wouldn't be here. If inflation had to end from a first order phase transition by tunneling out,
Yeah.
and those bubbles wouldn't lead to a smooth universe today.
Okay.
So we choose regions parameter space to rule those out. Those certainly could have happened. That's absolutely right.
Okay. So if I really was free to do
Yeah,
whatever I wanted, I would get those, right?
You have
So
some
now you're
regions
saying
where-
I want to get my CMD, so I should look at models of this type.
Yes,
Okay.
yes, that's right. So, and with the MCMC, we're not, well, what we're doing is we're filtering on matching the CMB. What else do you
Yeah,
do?
Right.
Okay,
Yeah.
But also you have some stochastic degrees of freedom there, right? To
Mhm.
choose and say, well, that is less likely.
in the
than
MCMC,
every-
that's right. Oh, absolutely, that's right. Here we were choosing, this was someone else's work. We were choosing by hand parameters that would make sure the field doesn't get stuck, doesn't have to tunnel out.
Right.
Because that leads to grossly different sky than we'd see today. In fact, it would-
It's almost anthropic.
Yeah,
Our universe, you want to extend our universe.
well, our CMB.
We
I would
want,
say-
we want, could this account, yeah, I mean, you could put it in anthropic terms. Could this sort of mechanism account for what we see, for us being here and what we see today? It could account for other
Well,
things
You
too.
can leave us out of it, right?
Yeah.
The CMB.
Our CMB, is what I
Right.
meant, yeah.
It's either, I mean, if you have to tunnel out, then it's, you're not worried about the CMB at the percent level. You're saying the Earth never formed, there's no Milky Way. That's a grossly different universe, cosmic history. And so you're right. So we're focusing on regions of parameter space where you don't get stuck. And in the MCMC, that's what accounts for why not everything's filled in. So some of these areas here, oops, if you're over here, you get stuck, for example. That's not in our likelihoods because that won't match the CMB. So these regions are regions that are going to succeed in matching things we know we have to match. We didn't put those in my hand, but we're filtering to say these are the regions we want to focus on for what could do that and give us the black holes. And if you're really out here on any of these parameters, then many things look wildly different. So, yeah. So I'm not trying to say this will land you there all the time. We're saying we're starting with what I would consider generic ingredients and finding non-trivial regions of parameter space that will do it, not everyone. Maybe that's the more
So
fair way to
it's
say it.
plausible, right? I mean, it's plausible.
This part makes me happy because if it was just a delta fund, we found one set of parameters, one of which is fine-tuned to some rigid, because well, okay, that's not any better than a single from the toy model. The fact that it really is some residual play, right? There's a little bit of give because I think of that attractor dynamics. That's what it lets you do this in not every place, but not only one place.
Any other questions? Yeah.
So do you expect these to bound up
not to be bound up now in galaxies, or are they uniformly distributed?
Oh.
Do they have velocities, the pebbles?
Good, thank you. So these would be consistent with essentially cold dark matter. And so one could add more features if one wanted to, but we were just trying to get an abundance of cold pebbles. And they will cluster gravitationally, doesn't mean they're usually open, you should have halos, and they should form halos. So they should do things that, WIMPs or axion light, they should do things like cold dark matter should do.
They should patch on completely to CDM.
That's the idea. And again, it comes down to the fact that they're, in terms of physical extent, they are essentially like elementary protons. So they would be, their mass is much, much higher than WIMP, presumably. But their spatial extent is still, smaller than a difference.
Could you have Earth-based PDH detector?
Yeah, but this is the problem with all the direct detection, right? We're far away from the galactic center, so the expected density would not be very high to begin with. And so these could pass through. Yeah.
The same as predicted for a wimpy CDM.
I think it would be, or the Olympics. Maybe we really funded to wonder about what the difference would be. Maybe let me turn it around. That deserves more thought. That's something that I've been kidding. Would detection signal be different for, let's say, chargeless proto black hole compared to a wave? So that'd be pretty cool to try to work that out. But in terms of the local densities we'd expect, I think it would be just like the cloud, there's a kind of diffuse cloud out by where we live in Milky Way. And good luck, right? Good luck to our friends. But you know better than me. It's really tricky to capture one.
But what will one of these things do? It went through me.
Probably nothing.
I think I won't feel it.
I mean, again, this would be something fun. Others in the room probably have a better sense of this. But if the short-shield radius thing is 10 angstrom,
Yeah.
and we say, and if I just think perturbably, I take a short-shield metric, and I say I'm 10 short-shield radii away. What do I feel? And if that 10 short-shield radii away is still within the size of less than one atom, then I don't think it's going to be a catastrophic event. It could be. Maybe I'm missing things.
No, it's weakly interactive, but it still has gravitational
Yeah.
field.
Right.
Oh, sure. That's
Right.
right. That's what I mean. If I imagine doing a perturbative expansion of my short-shield lineup, and I'm wondering, what am I going to feel 10 or 100 short-shield radii away from this thing?
I think it's the size that really makes it up.
So you're saying it would be a tidal, the gradients? Or,
Yeah.
But I think it could be some quantum lensing effect.
Characteristic velocity and 10 short shield away
yeah,
is still, C over root 10 or something. That's a huge velocity.
I see.
And,
Yeah, okay.
Yeah.
if this thing is going through me at 300 kilometers per second, yeah, my guess is it'll cause havoc.
Oh, yeah,
It would also be
I've done this before, like you see these black hole movies,
Yeah.
right? And they make black hole in a lab somewhere,
Yes.
right? And like things were getting sucked into it,
Right.
like electricity flying all over it.
But from 3 towns away, right?
No, but you do go through the math, and it's like, if you had a few trillion kilos, or something like that, it's like a trillionth the mass of the Earth. It would like uproot trees and things like this. It's still subatomic, but it has like a big gravitational
Okay.
field.
That's why we don't and Lux are hoping for trillions of kilograms.
All I'll say is that would be a fun thing to work out.
It's really hard for it to eat, but it can really just work.
That's a cross section. Yeah, right.
Yeah.
Yeah, so, okay, so hopefully we won't encounter this, Ramesh.
Yeah, I'm now praying, yes.
Maybe it's not.
I'm hoping you're wrong.
I tell you not to worry, they're telling you to worry terribly, so I don't know what the answer is. We've got to think about it.
You do both simultaneously.
Right, don't worry about it. Hold on that for 3 years. Yeah, please.
Hi, sorry, I was just wondering if you know about the future of these videos in real time.
Oh. Good, yeah, they could, although again, that's a great question. So if I go back to this here, it's a little smaller. So certainly smaller ones, they're expected to undergo Hawking radiation and for evaporation. We're choosing ones in this window such that they wouldn't have exceeded their lifetime yet. So the lifetime for evaporation would be longer than a Hubble, longer than 13.8 billion years. That's part of what sets this orange curve. So they would be evaporating today, they would just presumably wouldn't be even near the late stages. So they wouldn't yet be shooting out these highly energetic, radiation particles. Presumably, that's what is setting this shape here. But they would still presumably be active emitters, just not in a way that's going to upset current observation patterns. So they should have a finite lifetime, just by design longer than the current age.
I think it's time to wait our speaker again.